Hello everybody and welcome to a kind of different Houdini tutorial. Today we are going to talk about noise basics in Houdini. And the thing with noise is that we can do a lot with it. There's a lot of things such as attribute VOPs that once you dive inside you see a bunch of different nodes such as flow noise, curl noise, Antialias flow noise, and you might be a little bit overwhelmed about what they all do and how they're different. So I thought it might be fun to do a little bit of a deep dive on the internet and not necessarily go through Houdini and build something, but talk about the basic underlying functions of these nodes. So let's dive inside and get started. So let's talk about something first. I'm going to walk through the nodes and their different types of noise as we go along, and then we're also going to reference these tabs up here you see in Chrome based on what type of noise that we're talking about. So let's start out with the attribute noise SOP. Actually, before we get into the theory, I just want to skim through the different types of patterns of noise so you can see visually how they're a little bit similar before we actually talk about the science. So skimming through, you can see all of them represent a gradient where they go from black to white. And in between that black and white, you get grayer tones based on the different types of noise. So if you look at this one particularly here, which is on input 3, which is, I believe, the Antialias flow noise, you can see that it's very, the compression ratio for the gradients is very different from the other ones. And it may not be fitted in between a value of 1 to 0. Meanwhile, if you look at input 0, which is cell noise, you'll notice that it creates a lot of banding. So by adjusting the bands, you can see different things start to happen. So you can just see visually that they're very different, but the majority of them represent cells. And the reason that happens is that noise particularly revolves around where the points are in 3D space, and then it calculates the distance between those points and then creates a gradient based on the locations of those points. So if you zoom in right here, you can kind of see this little tiny smudge on the screen that I'm circling. The brightest part of that smudge is actually right centered around this dot, and the darker part, if we go over here, is another point over here. So you can kind of see it's created like a gradient in between those two boxes. So based on what type of noise you are using, it will calculate that distance function differently. So let's dive into the math. So starting with the attribute noise SOP, we'll talk about Simplex Noise. Similar to Turbulent Noise, it has fewer artifacts and has more improvements from a classical noise function. It can be scaled to higher resolutions than regular noise and lower complexity when rendering, and also less render time. It is a continuous gradient, and it was first created by Ken Perlin in 2001, and he was also the creator of Turbulent Noise. The cool thing about Ken Perlin is that he's won numerous awards. If you skim down here to my other notes, he is responsible basically for revolutionizing the texture industry. He has received numerous awards in the field of computer science. He has many other achievements besides creating noise patterns. He is a professor in the Department of Computer Science at New York University. He's also founded their Media Research Lab as well. And he has been honored with an Academy Award for Technical Achievement for Turbulent Noise in 1997. And he's also presented at SIGGRAPH in 1985 about Turbulent Noise. So without Ken Perlin, we probably wouldn't have the majority of, textures and fractal noise and shapes that we were probably used to in our software. The next one that you might notice in an attribute noise SOP is Sparse Convulsion Noise. So traditionally, this is a type of noise that uses something called Sparse Gabriel Convulsion. This means it's based on random numbers. So usually, if you were calculating the distance between a number of points, you'd go let's say, so if you were to picture a line in space, and that line had 4 points on it, you'd calculate 0.1, 0.2, 0.3, 0.4. But in this case, because it's sampling random numbers, it wouldn't sample all of those numbers. to calculate the gradient. It'd pick a bunch of random ones and then do it that way. But it also samples these numbers sparsely. So just pick, again, as I said, picks them up at random. So it doesn't sample them all, and this type of sampling is known as white noise. But it can also be computationally expensive. In Houdini, sparse convulsion noise is similar to whirly noise and is based off patterns off of turbulent weights of the closest points on the geometry. Turbulent flow noise. This type of noise can generate non-repeating patterns. It operates in the same way as turbulent noise. Turbulent flow noise is designed to create 1D or 3D patterns based on 3D data. So it tells patterns over a set amount of 3D space and is customizable based on its offset and frequency. So because this turbulent flow noise is non-repeating pattern, it's really great if you really want textures that don't repeat themselves and you're just jagged and kind of like terrain. So it's pretty good like that. So regular turbulent noise. And this is pretty much the most important noise type you're probably going to learn for any 3D software because of what Ken Perlin has made from 1985. Almost every type of noise in Houdini is somehow based around Turbulent noise. So understanding how Turbulent noise functions and works is very important to understand how other forms of noise functions work. This noise is based on gradients. It takes the gradients and calculates the vectors on the geometry it is going to be projecting the noise onto, and then it computes a dot product function between the sets of gradients to determine a pattern. It is also related to a latest gradient noise pattern, and it was first invented in 1985, as we've already mentioned, by Ken Perlin. It is a standard noise pattern that is used in almost every type of computer graphics software. It is mainly used to create natural and chaotic textures. It can be used as a 2D, 3D, 4D function to create patterns. In Houdini, Perlin operates pretty much as described above, but the improved function for it in Houdini sums up the octaves of the noise pattern in a range between 0 to 1. In Vex, you can call this noise pattern with the function O noise. So a cool thing before we go a little bit further. So looking over here at this tab, Turbulent Noise, you'll notice that, pay no attention to this title of the page, but I just want to bring attention to it. If you wanted to call these noise functions in Vex, they have string values that are relations to these variables right here. So if you wanted Turbulent Noise, you could call it as B noise because of Turbulent Noise. Original Turbulent Noise is O noise, so original noise, and so on. So if you didn't want to put down a VOP, you could also do it in Vex. So going back to Turbulent Noise, there's also the original Turbulent Noise function in Houdini. The original has less efficient capabilities and its bounds are between -1 to 1, so you will have to use a fit VOP node to center it between 0 to 1 if you want. You can still call it in Vex with the function we just described. So alligator noise. This is similar to whirly noise, which we'll talk about shortly. Its bounding regions are between the numbers 0 to 0.5. You can call alligator noise in Vex by using the function A noise. It creates very jagged textures. So if we were to go over here to our unified node little tab here and skim through the options, you can kind of see an example of what alligator noise looks like. It kind of looks like little tiny hills. So as it describes, it's again built to look like alligator skin. Though I'm not sure if that's really what alligator skin looks like. But we'll jump back into our notes. So fast noise in Houdini. In Houdini, this noise is a variant of Turbulent Noise. It still uses the same algorithm, but is faster. It also creates a different variant of Turbulent Noise with our larger bumps. So that's one of the reasons why it's called fast noise, because it's a faster version of Turbulent Noise. So F1Whirly Cellular. Whirly Noise was first created by Stephen Whirly in 1996. It is used to create procedural textures and patterns. This basic formula creates a pattern that resembles cells or stones clumped together. So again, based off of the points in space that I mentioned earlier. In Houdini, F1Whirly Cellular Noise is designed to generate patterns that resemble waves, plant cells, or basic landscape features. So one of the questions you might ask yourself when you're in Houdini is going, why is there an F1 and an F2 Whirly Cellular pattern? Same goes in Manhattan F1 and Manhattan F2. Well, this is the cool thing. So F1 is a variant of a Whirly Cellular pattern, and F2 is a variant of a Whirly Cellular pattern. So basically, they're just variants, and these are just the names for the variants. The F stands for function, so this is function 1, and then function 2, if that makes any sense. So F1, F2, F1 Whirly Cellular. In Houdini, this Whirly pattern follows the same basic structure as a regular Whirly function. However, this variation is designed to produce patterns that produce very blunt and jagged features, almost like a soft, pointy stone. So if we were to jump into our unified noise here and go down to it, kind of looks like that. So you can see the two differences between the two. One looks very cratered-like, and the other one is very cartoony mountains, really. So you can see there's huge differences in the way that they are calculated. Uses a function called Chebyshev, might be pronouncing that wrong, distance calculation. It is a great pattern for generating a very rough random noise. And another variant to this pattern is the F2 pattern. So in Houdini, this new noise is the same type of Chebyshev Whirly Cellular. However, it adds more variation and more randomness into the noise. So again, we can take a look at it and go down here, and that's pretty much the same thing. The documentation has even more noise types listed in it, but you can even discover more if you go into this little website right here done by Stanford Education, which is procedural noise categories for 3D representation and computer graphics. So they have the noise types that I won't necessarily cover in this lesson, but they have lattice noises, value noises, gradient noises, and pretty much every kind of noise texture that has evolved over the previous years, and how they've continued to evolve versus how they are related to each other. So you can kind of see how the circular Gaussian kind of goes into a radical sine, and you can see the sister product to a radical sine wave is a kernel Hyatt. So if that makes any sense, that's kind of how noise patterns work. So jumping down to our attribute VOP noise types. So yeah, taking a little look at cell noise, you can see it creates these banding effects. And if we jump into here, it's kind of originally designed to look like cells, but if you it really depends on what you add this node to. In this case, it's pumped into a grid, so it's not really going to do much. And there's other factors like fit nodes that you can put down on it. If we were going to put this on a sphere, it would look a little bit different, but generally it should keep the same pattern. It won't appear on primitives because we need to turn this to polygons. But if you were going to do a polygon mesh, put more stuff on here, make this bigger. Just so you can see it better. Turn off that. You can see that it's got like a very overarching circular pattern on it. So yeah, it really depends on what type of geometry you've plugged in for your noise to behave with. And again, you can customize that pattern as you see fit. Antialias noise is very special because there are two types of noise types you might also encounter in Houdini, and that is alias noise and anti-alias noise. Anti-alias is a little bit different than alias noise. The only factor that differentiates between the two is that anti-alias noise smooths out any jagged edges the pattern might have and averages the colors against the pixels. Alias noise does not do this, so you can kind of think of anti-alias noise as the texture-friendly version of noise. In Houdini, this noise type allows a fractional Brownian motion to compute noise patterns. So again, that pretty much applies to any type of VOP that uses Antialias Noise. It creates banding patterns that are based off of this fractional frequency, and the max octave parameter on the VOP node controls the number of iterations on the noise. So Antialias flow noise, this node operates in the same way as the regular Antialias node. It uses fractional Brownian motion to compute its patterns, but it also adds flow noise into the mix. Therefore, the node has extra parameters for this to function. The flow noise also adds more detail on top of the Antialias noise and also affects the frequencies of the noise to make them darker or lighter than they would usually be. So yes, Antialias Noise is a bit newer than Alias Noise, and it's kind of more texture friendly. So a curl noise is used in a lot of fluid simulations and for a lot of atmospheric studies as well. It is used for modeling turbulent flows because its ability to mimic large storms or high intensity areas. It's also great for generating velocity fields. So if you saw my presentation a while back for clouds, I mentioned curl noise a lot because it's used in a lot of cloud functions. It's used in Jupiter simulations of Jupiter, pretty much anything curl noise is used for. It really helps visualize pretty much any presentation better, and therefore it's used a lot in the scientific field for visualization purposes. So if we look at this study right here from the University of British Columbia, we can see that curl noise is used a lot in procedural fluid flow, and you can kind of see the patterns right here as well. A really good example I'll bring up, just give me 1 second, of curl noise is actually in simulations of ocean waters. So if we take a look at this simulation of the southwestern Indian Ocean, you notice right away that, guess what it has? It has curl noise. And you can pretty much watch the simulation and the patterns just repeat itself, especially in the lower left-hand corner of the screen, where you see the incredibly turbulent flows of those curl noise operating. It can create some very dynamic results, and it's very versatile for noise. So curl noise is also used in Houdini. In Houdini, it uses a Turbulent Noise function to operate. It generates 3D noise and has 4 parameters for you to control the noise shapes even more. And these inputs are step size, surface effect radius, distance to surface, and surface normal. And you'll notice that I've added these little brackets here. So H, D, dis, and N, and these are the attributes to represent those inputs. So those are what you would call them in Houdini in VAX4. So looking at flow noise. Flow noise is also used in a lot of scientific flow studies. So regular flow noise is the opposite of Turbulent flow noise. It does not repeat the patterns it generates in 3D space, but rather it generates a whole series of random patterns over its set end space in the software. Houdini, the flow noise VOP, has an extra parameter that allows you to control the flow of the patterns. This pattern rotates the noise vectors and affects them in the noise's space. Outside of Houdini, this is used a lot in calculating Bernoulli's principle, or flow rates for liquids, shear waves, and aeroacoustics. So this in combination with curl noise can generate some very nice simulations in water for you. So periodic Turbulent noise. Woo! This node is sort of the opposite of normal Turbulent noise function. It creates easy tileable repeating patterns. It doesn't really work well with other parameters such as turbulence, roughness, or amplitude. This node in Houdini operates by using Poisson distribution to scatter points across the surface. It is not anti-aliased, so it has a few jagged edges in its patterns, but its main pattern appears to be cells. When calculating the distance between points, it has 3 methods it can use. These methods are Aleutian, Manhattan, and Chebyshev. It also operates on the same operating system as Swirly Noise. So now we can jump over to Turbulent Noise. So Turbulent Noise in Houdini is designed to output multiple noise types. These noise types are Purlin, Sparse, Convulsion, Alligator, Simplex, and much more. So if we go over back to our Houdini tab, you can see that it's basically a periodic noise operator, or whirly noise operator, or periodic whirly noise operator, depending on what you really want to output. So it's up to you. And if we jump into Houdini and we try and find this node, because I have it here somewhere, right there, we can choose what type of noise we want to operate on, and as well as what type of noise we want to generate. So, because this is the last output, and we can switch it over to our sphere, you can see that it's got some very nice cell patterns right here, and that's because it's on Alligator Noise. But if we switch it over here, you can kind of see it change between the couple of types. So the higher the amplitude, the more intense it's going to be. The lower the amplitude, softer it will be. Pretty much like that. So whirly noise. So yeah, this is one of the most oldest computer generated types of noise. Whirly noise creates textures of stone, water, and biological cells. It randomly distributes patterns across points. It tries to mimic Poisson distribution as much as possible, which is basically cell divisions. And it calculates the distance between points and then creates gradients based on the calculated distance. So what I mentioned at the beginning of this lesson, F1Whirly wrote this algorithm in his paper, a cellular texture-based function. In Houdini, whirly noise can be controlled through various noise types, but also through the Whirly Noise VOP node. It is not anti-alias, so it isn't too great with textures. But if we jump over here to the Whirly PDF, which is his original paper that he wrote, you can see that it's 3 pages long and it's not too bad. But it basically describes how he created this noise application, and I will link it in the description of this video so you can take a look. Another cool thing I want to mention before we go even further is the bookofshaders.com, which does talk about Simplex Noise, Turbulent Noise, and Whirly Noise really well. And it talks about how you can write your own functions for it, so you can just copy these, and based on where you are, you can see how this would operate, and you can download the code as well and the artwork, which is very interesting, and it's also incredibly helpful if you like creating your own textures and learning the mathematics behind them. So yeah, there we go. There's our cellular noise of how it usually operates if you want to animate it. So Voronoi noise. Voronoi noise is based on Voronoi patterns or diagrams. These patterns are cells based off of Delaunay triangulation. So if we look back at the Book of Shaders pictures of those cells, those also operate on Delaunay triangulation. The noise is controlled by the number of cells in the calculated space. So the less cells they are, the bigger the cells are going to be. The more more points or more cells, the smaller the cells are going to be. In Houdini, there's a Voronoi VOP node that generates this pattern, but there's also other ways you can make it in the software. It is a heavier form of noise and does need some computational effort to calculate. In Houdini, the unified VOP node has a lot of functions. Unified noise is a mash of many different pattern generators, and these generators contain fractal, bandpass filters, and folding. This allows you to generate many different abstract results with the node. It offers the most patterns in Houdini to be that are normalized between 0 to 1 or -1 to 1, and these noise functions sometimes give artifacts or an area of static results around the offset 0. So if you look at the very center of the grid, you might notice something a little bit off. So you might always want to begin designing your noise offsetted so it doesn't generate non-zero results or values. So if you take a good look at the unified noise documentation, you can kind of see these little patterns that it creates based on some vectors. So if we zoom in, we can kind of take a look at them. So Whirly Cellular, and based on the different types of frequencies, you can generate fractal patterns and general like craziness. So again, Turbulent Noise will create these very wavy-esque patterns. And then Alligator Noise has gotten these very cute little indentations, almost like the bottom of the seafloor. And if you look at flow noise, oh wait, that's Jupiter. Ta-da! So like there's lots of things you can do with this node, and it's probably the most useful VOP node you can ever use. So I highly recommend using it. So the unified static node is exactly the same node as we just discussed. However, the noise and fractal type of the VOP cannot be changed and are set as constants. So their values are a little bit more finicky to manage. It is faster to optimize than the unified noise VOP, but it doesn't work too well inside of HDAs. And the next noise type is curl noise 2D. This noise allows you to generate divergent-free noise in 2D space. It adds curl noise and Turbulent Noise functions together to create noise flows around a given object. It also has the same inputs as the Turbulent Noise operator, so the node is very customizable. Pyro noise. This really isn't a noise generator at all. It's more of a kind of icing to your current node or noise node that you're using. This node multiplies values on top of your unified noise VOP. It also allows you to convert your noise into a vector or a float depending on what works with your pyro simulation. This also makes the noise easier to control in an interface setting. So if you wanted to promote noise parameters to the top, this would probably be very good for you to put down. So a mountain sop. We all know what a mountain sop is. If we jump back into Houdini and we go over here to our little mountain noise, you can kind of see that it's generating patterns already based on what I told it to generate. And it is very much position based, so it's based off of point positions and based on octaves. You can see the number of passes that it's doing and a number of iterations it's doing on that noise type. And you can pretty much choose any type of noise type that we've just previously discussed. One we haven't discussed yet is Sinoid. I think I'm pronouncing that correctly. This one is based around sine waves. It's pretty straightforward, but it's not actually the type of noise. It's more used as a diagnostic tool than anything else. It outputs between a range of 0 to 1. Another thing you might notice on your little noise settings is that you see these terrain, hybrid terrain, and standard settings, and they might not do a lot depending on what you're doing at the time or what type of setting you have your noise set to, but depending on how you switch, but when you switch them over, you'll notice that they do have some differences, such as hybrid terrain is a little bit more round, terrain has a little spike at the top, and standard is just all out chaos. So what makes them a little bit different? Okay, so I switched over to a different type of noise, and you'll notice that if we look at these very sharp valleys on hybrid terrain, you see these little kind of pokey things. And if you switch over to terrain, you can see that it smooths it a little bit out, which is really, really great. I'm just going to tone that a little bit down so it's less chaotic. So hybrid terrain, this version is similar to the terrain function but does not smooth out any valleys, just adds more chaos or keeps chaos. Standard FBM, the standard pattern adds a pseudo-random noise into the mix. That means it just adds a certain amount of statistical randomness into the equation. The FBM stands for fractional Brownian motion, which is the motion it used to calculate the pattern. And we've already mentioned this kind of before in other noise types. Terrain, this function is mainly used for generating terrain, as it removes any noise from the deep valleys that your terrain has generated and is great for generating mountains. So that's pretty much it for all the noise types in Houdini. I hope you enjoyed this lesson. I know it wasn't quite as interesting as a regular Houdini tutorial, but I just wanted to talk about it because I feel like this topic isn't covered enough, especially in a 3D landscape. So I hope you enjoyed this tutorial. My name is Kate, and I'll see you in the next video. Bye!